This talk is on a way of looking at quantum mechanics, which for a long time was not popular, and I'm hoping to bring some change in that and explain to you how I think about quantum mechanics, which is indeed not exactly how normally people talk and think about it. So we are used to this classical theory, planets and stars, billiard balls, and so on. And we know exactly the effective laws of nature by which they move. And we call these laws of nature deterministic, which really means that there's only one truth, and the truth is described by the coordinates of all the objects that you're talking about. And the way these coordinates evolve in time is given by very precise classical equations. However, on the atomic scale, this is no longer true, it seems. So at the atomic scale, the only laws we can write down are quantum mechanical laws, and they seem to be not deterministic. So even if you know as well as you can ever dream of the initial states of all the atoms in a certain process, then you will not find that the laws that tell how these atoms evolve will be referring only to the reality that you see, but there's something else going on. You could call it a hidden variable, and there's something not right with the deterministic viewpoint. So it so happens that it is about for 100 years now that physicists know what to do. And they call that the Copenhagen Convention or Copenhagen interpretation. And the answer to the questions is, don't ask any question, just follow the rules, do the calculation. Here is the Schrödinger equation. And if you use that equation, you will find everything that you want to know, and there is not more to be found. That is in short, the Copenhagen viewpoint, and it made a lot of sense. So people who work with quantum mechanics could use that rule. They found they could, under all circumstances, compute what they want to know, and the theory works as well as you can ever expect it to be. But when particles move, say, in beams towards each other and they collide, the collision is precisely described by quantum mechanical rules, but the theory never predicts you exactly in which direction the particles will scatter, but the particles will scatter randomly in all directions. In some directions more than other, but you can't say they'll go in any specific direction. So that is the situation today, and to some people, including myself, this is not quite the ideal situation. It is a little bit like the situation you have when you predict the weather. So when you predict the weather, you can say with certain probabilities what the weather will be tomorrow and the day after, even what the weather will be weeks or months after now. You can write down a probability distribution, but you cannot say exactly what the weather will be. However, in case of the weather, at least what you can say, we know which laws are responsible. They're just too difficult for us to solve, because every single atom in the clouds, and not every single cloud, and every status of the weather at every point on the planet Earth must be given. And then in principle, you should be able to predict the weather much more precisely than you can now. And the more precise statements you can make about the initial state, the better the prediction becomes. But for atoms, this is not the case. So, and according in particular to John Stuart Bell and many others, an aspect who actually did the experiment, they say, no, it doesn't work. You cannot predict the future from what you know now, no matter how accurately you describe, no matter what kind of data, it will not work. They give a so-called no-go theorem. Now, when I hear people write down a no-go theorem, I know that they're just missing something because it hasn't happened before again and again that someone writes that something is impossible. You can try whatever you like, but this solution will not work. Then you know only one thing, which is that the method used wasn't right. They didn't think of something. And the same thing here. People who say that there is no way to interpret quantum mechanics in terms of deterministic processes, then they haven't taken into account everything. And my bottom line will be, and I'll say that precisely, if you have a deterministic theory, it must be deterministic all the way. So everything must be deterministic. You should not allow for any chance to occur. As soon as you do that, your theory doesn't work anymore and everything becomes unpredictable. So that will be the bottom line. I say it now just to give you a sketch of what I'm going to talk about. And there are clues that you can use to understand in which direction to search for a better theory. And one clue is given, I should say, if you don't understand me well, I can imagine it's a long distance for the signals now to travel. If you don't understand me for whatever reason, please shout and I'll try to talk lower or clearer. So I would hope that is clear. So there is an interesting clue as to where to search for a better description of quantum mechanics in terms of deterministic laws. And that is by considering an unstable particle. In particle physics, but also in nuclear physics, there are many particles or states of particles and states of atoms which are unstable. After a certain amount of time, the atom decays by emitting a particle, or a particle can decay by splitting in several other more stable particles. We call those unstable particles. And the unstable particles are known to obey an exponential decay law. The exponential law says that at all moments when you look at such a particle, the probability that it will decay right now stays the same. That probability can be very small, it can be very big. The particle can have an average lifetime of only nanoseconds or less, or the particle can have an average lifetime of billions of years or more, but they all share the same property. The exponential decay law is described by an exponential curve. How can you square that with determinism? Suppose that you have a particle, but you imagine the particle to contain a clock. The clock is ticking, and the clock ticks from 100 to 0, 100, 99, 98, 97, and so on. It goes all the way to 0. And when the clock says 0, the particle says bam, and it decays. That is not an exponential law, but that such laws are usually not found for decaying particles. So particles don't carry a clock, they decay spontaneously with a probability that remains the same. And the question you can then ask is, can you square this with determinism? And the answer is absolutely yes. By itself, such a decay would be a normal thing to expect in a deterministic theory. But you have to remember one thing. The state we call the vacuum state, which is a state with no particles present at all, that state is not empty. There's lots of things going on. In fact, what we call vacuum looks more like white noise. Think of a television set that's not tuned in to any broadcasting station. So the television set just gives a screen with which is blinking in all states. That's we call that vacuum fluctuations. And if you assume now that the vacuum state actually contains very, very many fluctuating data, which fluctuate essentially randomly, then you can say, okay, a particle feels those data only when the surrounding data or the data surrounding a particle take a very special value, the particle suddenly decays. And that it is exactly the way you can describe a decaying particle. And that picture works excellently qualitatively. But now the question is, okay, if you have this insight, then what is that law? What is the special state that the vacuum has to be in for this particular particle to decay and for other particles to decay? All different particle types decay at their own preferred rate. But the question is, how do we fill in the details of such a theory? And
question?
Yes.
Yeah, can I? So let me check out whether I understand the statement. So based on some chaos or some chaos mechanism, you will derive some H bar and some uncertainty principle, some fundamental principle of quantum mechanics, or some that.
Yes. So what you say is exactly right. My aim is to derive such a law. Now I have to add immediately, to get the details right is extremely difficult. And I have not even come close to doing that. So if you think I have a ready, full prepared theory and you can switch it on right now to compute anything you like, no, I have not done that. But what I can do is explain how such a theory will work, how it should be set up.
Okay, thank you.
I hear some noises. I don't know what they come from. Okay. So the prototype and the way to think about such a theory is called a cellular automaton. A cellular automaton is, you have to imagine a grid. This grid would fill up the entire universe. The sizes of the grid are extremely small, smaller than anything we have been able to study in physics today. You can make a combination of the fundamental constants of nature, the speed of light, Planck's constant, and Newton's gravity constant, to find a unit of length which is extremely small, even compared to particles that we know. And it is probably that scale at which we have to think, about which we have to think to understand this cellular automaton. And what it basically is on the grid, at every side of the grid, there are certain data indicated here in this picture in terms of triangles, spheres, or other objects. In this picture, I gave them different colors, just to indicate that every single lattice site can be in a certain state. I call that a state, but this time it is a completely classical state. Some people had the same idea about the cellular automaton, but then they fill in quantum equations for the cellular automaton. I'm saying no, those won't eventually be quantum equations. They will be classical equations. Very important to remember. That is my statement. But I have not yet, or not at all, been able to specify the details of these states. It is probably very, very hard to do so. To do that right, you have to know a lot more about the standard model. The standard model that describes the particles today as best as we can using Schrödinger equations, using quantum mechanics. But eventually, I'm saying no, the correct equations should be without quantum mechanics. If you can write down such equations, you will be able to be in a state that you will understand much more. And I claim there will be an important outcome of these investigations, which is the statement that, yes, in principle, we should be able to calculate the constants of nature in the standard model. Today, we know that the standard model contains more than 20 constants of nature. Those constants of nature have to be measured and put in by hand in the theory for the theory to work. We have no way of computing these constants. My claim is, if we understand the problem I'm talking about, if we understand that right, then we can actually calculate those constants and we can have something to check the theory with experiments, because those constants will be computable and we can compare them with what has been measured. There will be 20 measuring points which should allow us to check the theory. But I am not even close to that kind of stage in formulating this theory.